Defining AI logic in a deep neural network, DNN, involves structuring the network architecture, specifying its layers, activation functions, and training methodologies to enable the network to learn and make decisions. Here's a breakdown. Pradeep K. Suri. Author and researcher. Network architecture. 1 input layer, defines the input data's dimensions and format. 2 hidden layers, these layers contain neurons that process the input data through weighted connections, applying mathematical operations, like matrix multiplications, followed by activation functions. 3 output layer, produces the network's final predictions or decisions based on the processed data. Neurons and weights. Neurons, these are units within each layer that receive input, apply weights, and pass the result through an activation function. Weights represent the strength of connections between neurons. They're adjusted during training to minimize errors in predictions. Activation functions. ReLU, rectified linear activation, commonly used in hidden layers to introduce nonlinearity and allow the network to learn complex patterns. Sigmoid or softmax, often used in the output layer for binary or multi-class classification, respectively, to produce probabilities. Others, like TAN, leaky ReLU, etc., used based on the problem's requirements and network performance. Training methodologies. Backpropagation, a technique where errors are propagated backward through the network, adjusting weights to minimize these errors. Loss functions, measure the network's performance. Common ones include mean squared error, MSE, for regression and cross-entropy for classification. Optimizers, algorithms like stochastic gradient descent, SGD, ATOM, RMSProp, etc., update weights to minimize the loss function. AI logic in learning. Pattern recognition, the network learns to recognize patterns by adjusting weights during training to minimize errors between predicted and actual outputs. Generalization, DNNs aim to generalize learned patterns to unseen data by avoiding overfitting, memorizing the training data, and instead learning underlying patterns. Representation learning, DNNs automatically learn hierarchical representations of data, extracting useful features from raw inputs. Hyperparameter tuning. Learning rate, batch size, epochs, adjusting these affects how quickly the network learns and generalizes. Regularization techniques, dropout, L1/L2 regularization to prevent overfitting. Network depth, width, and architecture, the structure and size of the network affect its learning capacity. Transfer learning and fine-tuning. Leveraging pre-trained models on similar tasks, transfer learning, or fine-tuning existing models for specific business applications without starting from scratch. In summary, defining AI logic in a DNN involves configuring the network's architecture, specifying activation functions, adjusting weights during training, selecting appropriate methodologies, and fine-tuning parameters to enable effective learning and decision-making. Thank you.